We have an interesting presentation today about how to use audio signals, specifically AES67, outside of a local area network environment. And giving the presentation today is Nicolas Sturmel from Merging Technologies. Take it away, Nicolas.
Let's talk about AES67 beyond the LAN, and especially the word beyond the LAN, meaning that we will talk about all the use cases, the different use cases that allow streaming AES67 outside of what it is used, usually the local area network. So those use cases are high quality contribution, meaning bringing audio into the studio from outside the studio, live concerts with musician support, which is what we viewed a lot during the pandemic, monitoring voiceover in multiple languages, which is what one of our customers, Eurosport, is doing a lot in Europe at the moment with 25 different studios for the 25 different languages. And of course, the cloud, because why not the cloud if it's cheaper? And these use cases went really, really in high demand during the last 2 years. Go figure. So at the AES, at the standard committee of the AES, the standard committee SC-02-12M, we decided to start a working group on defining the best practices of using AES67 over the LAN. And this came handy because when you compare to other audio over IP systems, some audio over IP systems are not really over IP, as they cannot really easily cross routers and accommodate subnets. AES67 by default is fully IP, so it can cross subnets, and this is the main features that we used as a support in providing help to the AES67 users of doing AES67 beyond the LAN. So the word beyond the LAN is chosen because we don't want to exclude anything that is not a LAN. Mainly the cloud is not a LAN as it is not local to you. And the WAN can have multiple different faces, be it internet or just a long distance connection that you use black fiber, etc. So in this group, we had a lot of contributions, and this was very interesting because we had academics, we had manufacturers, but also we had system integrators and users. So this gave us a whole view of the land of AES67 users and the needs was called AES R2021. It's even on the roadmap that you can see on the booth. So the question is, what is beyond the LAN? So let's look at the standard LAN. So you have devices, you have a switch, and you have a PTP master most likely. And then you have a gateway maybe to connect your LAN to something else. And this something else is another LAN. So you have a long distance line between those two lines. And when you look at the sizes of the LANs, typically a LAN is 10 meters, 100 meters. Long distance line is 10 kilometers, 100 kilometers, even 10,000 kilometers. So you have a huge level of difference in the size of those systems. And of course, you can have even more than just connecting two LANs. You can connect virtual devices in a data center, for instance, or you can connect endpoints of the go via, for instance, a 5G. Rather, let's see what defines a LAN and what defines other networks like WAN or the cloud. So a LAN is mostly layer 2, and this allows other audio over IP systems to actually use layer 2 features inside the layer 3 features to get better performances, but then not really able to easily cross the subnets. A LAN is fast. It's really fast and really small, and it is most likely self-administrated. You can do whatever you want on your LAN, and nobody will really care until you try to connect this to the other networks. On the WAN, it's totally different. It's mainly layer 3. You will have subnets. and you have varying speeds. If you are on the long distance connection, it's usually not the same speed as your local connection. So when talking ST2110, it's easy. You can have easily 100 gigs connection on your local connection, but having 100 gigs as a leased WAN connection is another topic. For the audio, it could be easier to have the same speed of connections, but audio contribution is often done via the internet, and then the speed problem arises again. You have long distances, so as opposed 10 to 100 meters on the LAN, you have a 10 to 10,000 kilometers of distances. And you have protocol limitations. You have protocol limitations because most likely you will share this one connection, you will share the LAN, the line, you will share the line with other customers and your line providers. Your WAN provider will give you limitations in what you can do on this connection, maybe even up to the fact that you cannot do multicast. And this is the case for the internet. Obviously, on the internet, you cannot do multicast. And then you have the cloud. And the cloud, I define it as S3++ because it's a very tightly managed network that is also layer 3. It's very fast and it's usually small in terms of sizes, but you have very few control on the infrastructure. And you are sharing traffic by definition, and you are even sharing platforms sometimes. So when you are trying to get performances we are acquainted to in the audio world, so milliseconds of latency, etc., it's harder to do on the cloud. So you see, I did put an hour of self-administrability just to show that, of course, the further you get from the LAN, the higher is the constraint on your network and on your administration. And then the higher is the need for open standards that are supported by every IT partner. Size matters in the sense that you have the speed of light, and speed of light is limited. And while you usually don't really care about the speed of light on a LAN because the sizes are really small, when you're talking about 10,000 kilometers, you cannot ignore that with a speed of 200 kilometers per second in fiber, 10,000 kilometers will cost you 5 milliseconds at the minimum. And of course, you have new equipment on the network. Instead of just using switches, you will have routers, or you will have media converters, and they may even cost you in terms of latency, and they may cost you in terms of delay to queuing, and maybe you can lose it. So never forget that the network was designed with the following idea in mind. I know when my data enters the network. I don't know when it gets out, or even if it gets out. So this is why we have TCP. But obviously, TCP is not a solution here, because TCP will only increase our latency of multiple times. So let's talk about delay and jitter. So you're on a typical LAN, and this is the packet size of ST2110. You have generally an expected latency of 125, 250 microseconds when transmitting data. So if we have a network that is 100,000 times higher, do we get a latency that is 12 times 5 seconds? Of course not. It does not mean that, because your delay is basically two parts. And there's the geographic delay and the packet delay variation. And the geographic delay on the LAN is really negligible. So those 225 microseconds, they mainly come from the packet delay variation, which is caused by the sending device and also by the network and the underlying network equipment. So on the WAN, it's totally different. The geographic delay cannot be ignored. And depending on the efficiency of your connection or on the performance of your WAN connection, you may experience that the packet delay variation is higher or lower than the actual geographical delay. So if you take the internet, for instance, you may have a 50%, 50-50 ratio. If you are leasing a line, a long-distance line, like the Switch broadcast company is doing in Switzerland, so they have their own network all across Switzerland, there the packet delay variation could be negligible, but you still have this geographic delay. So that has been addressed. Okay, but you also have the network topology. So the size of the network is not really the flying path from point A to point B. And you may need to go around given on the topology of the network you're using. So for instance, in France, we have a white spot that is not interconnected, and sometimes you need here to go from Bordeaux to Lyon, you have to go through Paris. And it's even the case with TGV, with the train. And this is because actually the fiber lines are buried with the TGV lines. So this may be a problem in terms of latency, because even though Bordeaux to Lyon is approximately 400 kilometers, the size of the fiber, the actual length of the fiber that will connect those two cities will be easily 800 or 1,000 kilometers. So we did a test. We did a test with the Ravenna guys during COVID, because we were so bored of not doing anything that we said, okay, let's try some fun. And we put a SRT, so stream reliability transport endpoint in the cloud, in AWS server in Frankfurt, one in Frankfurt and one in Virginia. And we exchanged streams between Ross video that was in Ottawa and our business center in Lausanne, and then with direct out also in Germany. And here we can see that we needed to configure 300 milliseconds of receiver delay to be able to receive this stream. And the receiver delay comes from the network, the geography, and also the SRT protocol that we will see just after. Of course, then, when you acknowledge there are delay on the networks, you also need to do synchronization. And synchronization is not really impacted by the delay, because PTP will correct the delay easily. It is impacted by packet delay variation. And the geographic delay is not a problem, but the packet delay variation is a problem, up to the point that some node cannot really synchronize on a highly jittered PTP signal. So you have to find solutions. And you can use synchronized mode, so only taking the frequency, and the video guys, they showed us that you can do a lot with synchronized mode. Who cares about the phase anyway? So this is a joke, of course. On some audio system, phase is really important. So you can still have the phase, but have a relax the expected accuracy that you expect on the sync. For instance, instead of using PTP, you could use NTP. Okay, with NTP, you will be 1 or 2 milliseconds away between the nodes, but when you are kilometers apart, what is 1 or 2 milliseconds anyway? You can use special boundary clocks with jitter rejection, and kudos to Mindberg for that, because they did some presentations of implementation of that. And you can also use synchronization out of the network, so with the GNSS PTP leaders. And this is actually what most of our customers are doing today, including Eurosport, that has 25 studios across Europe, that is with one grandmaster or one leader per studio that is connected, that is receiving the GPS signal. So how it's done, it's easy. We have the GPS system or the GNSS. You don't have to use GPS, but you have to use satellite sync. Then the PTP Grandmaster is receiving the GPS signal and distributing the clock on each side of this long-range connection. And then you can exchange the streams easily, given that you have enough buffer to accommodate for the delay given by the network. Okay, and then let's talk about using packets. So we saw that when going over the WAN, you have a lot of new equipments that have waiting queues, and since you are sharing the traffic, you will most likely lose a packet. So while it's rare on LAN, and it's so rare that I have yet to see one perfectly configured LAN to lose packets. When the LAN is not properly configured, of course you will lose packets, but when the LAN is correctly configured, you generally don't lose a packet. On the WAN, you will lose a packet due to network congestion, link failure, etc. So AES67 2018 doesn't address this problem, but ST2110 does, and we can also order techniques. So we have FEC that is widely used in audio contribution because it's compact, so it doesn't have too much delay, too much bandwidth to the audio stream. FSA is called forward error connection, so basically you just send correction data to accommodate the loss of 1 or 2 or 3 packets. You can use RIST and SRT, and now the IP showcase is present in RIST and SRT. Those are query methods that behave like TCP but with a timeout. So the simplest definition of RIST and SRT is TCP connection with a timeout. So SRT, for instance, is doing, when it sees that a packet is missing, it is requesting back the packet again. So this is why on the experiment I showed you before, we had 300 milliseconds, because basically with SRT, the rule of thumb is that you have a delay of 2 or 3 times the ping, which can be huge, but yet it's an easy way to gain quality in the stream transmission, because you basically don't add so much bandwidth to the transport. And of course, you are 2022-7. You send the same stream on different passes. This could be cool, but having really 2 different passes can be complicated, especially on the last mile. So when you are in the audio world, you basically don't have so much resources, and maybe up to the point of having 2 different ISPs, for instance. So the easiest way to deal with that is usually to lease the gateway. So it's an all-integrated, all-integrated solution that gives you a black hole, white hole type of infrastructure. It's basically a black box that you connect on both ends, and it takes care of everything that we used, that I presented before. And you can build your own gateways with open softwares, etc. And then this is what we did. So the experiment from before was done using an SRT gateway that was built from scratch with the SRT software, of course, and exposed on the web page that was running live during this presentation that was already almost 2 years ago. Okay, so of course, I didn't talk that much about the cloud, but the cloud could be seen as another network layer that is adding PTP, jitter, and delay. So the cloud could be synthesized or modelized as just a virtual WAN, but it's also using, it also needs to use different techniques and accommodate to different techniques. So VXLAN, encryption, etc. The use of unicast versus multicast, if needed. So cloud is a so wide subject that it should require its own presentation. then that's it. Why do you use protocol like RTP and SDP? They are built into AES67, they are built into ST2110, and they are the key to transmit streams beyond the LAN. And this is exactly the fact that you go over the LAN, but you stay layer 3. And the fact that those protocols are purely layer 3 and not at all caring about layer 2 is the key in achieving right performance, high performance, but of course you need special care, especially in terms of synchronization, to reach those performance. And really the solution depends on the performance of the underlying infrastructure and on your use case. And the use case word here is really important because you need to really analyze your expected performances to not try to overshoot in your solution. That's it.
Nicolas, thank you very much. We appreciate your time.